In the next few minutes, we are going to demonstrate an integrated approach to BIM modeling for infrastructure and transportation. We are going to evaluate a new road design, which we'll bring up in the RDV Site Navigator. The 3D CAD model was created by a road design consultant using Bentley's MicroStation and was exported as an RDV interactive scene. First, we are going to have a brief look at the model and see what types of information we can get out of it. We'll start off viewing the model in the RDV Site Navigator, which is particularly useful for general analysis and on-the-fly presentations. The project is a highway upgrade with 2 planned interchanges and an increase in the overall design speed. As well, the bridge design takes into account added room for improvements to the railway passing beneath. The model incorporates data from aerial imagery, surveyed ground data, GIS, and detailed CAD design in a flexible simulated environment. We may add in animations and make changes on the fly. Using the mouse alone, we can move throughout the 3D environment and easily look at any point in space, as well as evaluate what can be seen from an infinite number of vantage points while retaining all the precise design information in the same model. Specifically, we are going to look at the bridge system. A bridge is proposed for this project, which will be divided into 2 structures with a specified 90 km/h design speed. As the design option progressed, the Road Authority was interested to see if it was possible to optimize the design while evaluating the factors regarding required site distances. The decision to go with 2 separate bridge structures was taken to allow the phased implementation of the interchange as actual capacity was required. The implication in terms of the site requirements meant that the analysis had to be run on multiple configurations of the project to ensure that safety requirements were satisfied not only in the final design configuration, but during the phase stages of implementation. Therefore, in the first stage, only the northern bridge will be open and operated as 1 lane in each direction, and in the final phase will be converted to 2 lanes in each direction after the second bridge is completed. Note that the bridges are based on vertical geometry, including a crest vertical curve with significant positive and negative slopes, which in turn have an impact on the site distance calculations, which vary depending upon the direction of travel along the bridge. Here we have the RDV Road Safety Analysis module running. I'm going to open the 3D model of the detailed bridge design for analysis. Once the model is loaded, we can select a set of criteria files for the desired site distance scenarios to be evaluated. In this case, we are choosing stopping site distance for 90 km/h. We'll have a look at this specific file, which was set to the DOT standards. They can easily be developed or modified to any local standards. The computed distances for stopping site distance, varying based upon the slope, are shown and reflect values from the DOT design manual. Our initial run at the analysis looked at 2 different widths for the inside shoulder. Either 3 meters, which was the width originally proposed in preliminary design, or 3.8 meters, a width calculated by the geometric designer to address deficiencies for the required stopping site distances. After illustrating the obvious problems with the 3-meter option, a careful look at the 3.8-meter proposal indeed indicates that there may be room for optimization. Keep in mind that construction of shoulders wider than necessary, especially for bridges, can be quite costly. After these 2 initial simulation runs, we set up additional paths for our simulation at 10 centimeter increments to find the optimal solution. Notice that as the vertical slopes change along the alignment, updated values for site distance are calculated and evaluated automatically. Within a few minutes, all paths and configurations were analyzed, resulting in a recommendation to the DOT of a 3.4 meter shoulder, which optimizes cost savings while ensuring that the safety of the design is not compromised.